Hi, I hope you liked the previous presentation because I'm going to show you the same model again. But don't worry, this time it will be on the different physics. So the physics will be the cathode cooling. So what's happening after you lose the power on the potline for some time, and then the cells start to cool down. And what is the type of damage this cool down is producing on the cathode block? It was written by Alton Tabereaux, and I've done the modeling. It would be my pleasure to present it to you now. So the introduction is that there's many ways to damage cathode blocks and anodes by thermal shocks. One thermal shock is that we try to avoid is during the preheating of the pot. And when you put the new anode in the bath, you have some stress there. And then when you lose the power on the pot line for some time, and the pot is cooling down, there's some stress occurring in the cathode, and if the power shutdown lasts too long, you will get some cooling cracks that are, especially if you bring the pot to ambient temperature and then later on you restart, you will see that the cathode there's some cathode damage, cooling cracks that are there, and that will unrepairable, and they will have an effect on the ultimate pot life of the potline. So when we are modeling the cooling down, and when we are observing a cooling down physically, the cooling down, there's a important physics that's occurring is called thermal arrest. It is simply when you have a phase change between liquid and solid, the heat, latent heat, slow down or stop for some time the cooling rate. And this is useful because it slow down the irreversible when the time where it's impossible to restart the potline. And it is, of course, must be accounted for in the model. So it's happening when the bath is freezing, and during that period, there's no more temperature drop. So this is a sketch of the concept. And then you have some real measurement here. We have a pot was a measure in China, suffer a 5-hour shutdown, and then during that time, they observe the cooling down before the thermal arrest. Then there's a thermal arrest that lasted about an hour and a half, and then a second cooling rate after. And because that pot line was restarted after 5 hours, they did not observe the thermal arrest of the metal. That was observed in another set of measurements done by Reynolds. And this is the recorded and the reference. So it took thermal arrest for the metal occur about 24 hours and lasted for 4 or 5 hours at about 660 Celsius. So this is an important physical aspect of the cooling down. There's 2 thermal arrests occurring during the 2-phase change. Okay, now once we have reached the pot room temperature or the ambient temperature, and then we remove the stuff in the pot and we observe the surface, we can see cooling cracks. They are still open, and there are no sign of metal infiltration, so they are most probably occurring during or after the phase transition of the metal. They are still open at ambient temperature, like we can see on the left, about 3 millimeter wide opening, indication that there are still some unresolved stress in the cathode, and then the global system, now that is at uniform temperature, still have some still want to be open on the top surface. They are typically spread every block or every second block, like we can see here. So there's some cracks in after the first block in the joint, and after this maybe in or close to the second joint, and then 2 blocks later, another cracks. They are always oriented toward the direction of the cathode block. So in this case, we can see they are following the joint between blocks. Okay, so what about the physical property of the cathode block? In that paper, Alton did a very extensive review of the property that were measured by some researcher. We are not covering that in the presentation, no time for that. So I'm presenting only this table. That is a table 3 in the paper. And for semi-graphitic, we are, and graphite is almost the same. We are, for this paper, the number 8 megapascal is the critical structural strength. So we are assuming that in tension, the cathode block, if it reach 8 megapascal, it will crack in tension. Okay, now we are modeling this. So that's where the previous model is coming back. We need to have a starting point. The starting point is the operating temperature, and from that starting point we cut the power, and then we let in transient mode we let the structure cool down to the same ambient temperature that was present in operation for a duration 24 or 48 hours, and what I'm going to present here. And for 2 types of grade of carbon, 30% graphitic and 100% graphitized cathode block. So this is the final temperature after 48 hours of cooling. So the scale here is now stop at 673. So that's the maximum temperature of that pot after 48 hours of cooling. I can show you that in an animation. So I'm starting from operating temperature that was calculated with the steady state model that was presented in the previous presentation. And from that point, we simply let ANSYS compute the cooling down with no more internal source of heat and the same boundary condition for the heat dissipation. And we have, of course, now we have the bath and metal are thermal, and they have also a property to account for the latent heat of the phase change. So I will not continue this up to the end because I'm short of time. So this will continue to cool down up to 48 hours. And now I'm presenting only the temperature of the cathode panel. And this first set here, it is for 30% graphitic cathode block. And after 24 hours of cooling, they have cooled down to minimum 852 degrees with a thermal gradient of 311 degrees Celsius. And the next one is for the 100% graphitized. They are cooling faster because they are more conductive, but because they are more conductive, also the thermal gradient that is developing into them is less. So after 24 hours, only 154 thermal gradient. So you can simply see the cooling down of the temperature for that 24 hours. So I'm going to stop again. So now for this mechanical modeling I'm going to present next, I need to have some assumption. And my assumption will be that at operating temperature, in operation, there's no strain and no stress. And from the cooling down, the strain will come from the freezing or the change of decreasing of temperature. So my temperature for my thermal expansion will be negative, so I'm going to get the contraction, and that will generate some stress, especially because a gradient will develop. So I'm going to present those gradients. So this is the gradient I'm going to get for the 30% graphitic cathode block. So now I'm subtracting the current temperature after some time of cooling. I'm subtracting that temperature. From that temperature, I'm subtracting the operating temperature, so I'm getting a negative number. And now I'm getting different gradient because the operating temperature was not uniform. And then in that case of the 30% graphitic cathode block, I'm getting now at a maximum gradient of 136 degrees Celsius. And for the 100% graphitized, I'm going to get maximum 79 degrees of thermal gradient after 24 hours of cooling down. So that's the temperature. Those temperatures that I'm showing here, they will be used to compute the shrinking of the cathode panel. And from that shrinking and that the gradient in that shrinking, some stress are occurring, but that's not enough to generate enough to correct them. So in addition, as we have presented in TMS in 2011, we are also prescribing zero displacement on the vertical face of the cathode that are touching the cast iron in the slot of for the collector bar. So those faces, they are specified zero displacement on them. So even if they want to shrink, they won't be able to move. And that will create some extra stress in the top surface, and this time plenty of stress to crack them, as we're going to see. So this is the maximum stress we're getting for the 30% graphitic. So it is close to 9 megapascal, so it's way above 8. So that's a prediction of cracks. Now the stress that are displayed here are in the X direction. That's the long direction of the cathode panel. It is almost the same if you ask for the principal stress, S1 in ANSYS, it's the label. You get the same picture. So the principal stress, they are aligned with the X direction for this problem. So the next is the animation of the result for the 100% graphitized cathode block. They are getting to 8 megapascal later, and after 24 hours, just barely starting to reach that intensity. So the model is predicting that the 100% graphitized cathode block will be not spared, but the cracking is a bit delayed. And this is a graphic showing the full evolution of that maximum stress for up to 48 hours. So we can see that we are crossing the 8 megapascal limit at about 20 hours. Of course, this model is not forming cracks, so it is even if the property of this cathode is quasi brittle, we are modeling an elastic only. So we are not forming cracks, so the stress are continuing to increase. So it's not so relevant what's happening above 8 megapascal anymore. But what's important is the prediction that at about 20 hours, we are reaching the limit of where the cathode will start to crack. So if we can, of course, if you can, you will not be able to restart. So if you pass the limit when you cannot restart, you will have to endure the full damage of your cathode. Conclusion, we have developed cooling model, and we have analyzed with that the crack formation, well, the stress prediction for two type of cathode grade, 30% graphitic and 100% graphitized. The mechanical model is very oversimplified, but we have to do some assumption to be able to compute something. We are assuming zero stress, zero strain at the operating temperature. So we are assuming that some creep has occurred in operation for long enough time so that the lining is settled down to some condition. And then when you start to cool down, some stress are occurring due to the thermal gradient and to the boundary condition. So the assumption that the collector bar will prevent any displacement of the bottom part of the cathode. We are predicting different rate of cooling down for graphitic, 30% graphitic and graphitized, and different level intensity of thermal gradient. But since they are both subject to the same restriction of displacement, the same type of stress occurs in both type of grade. The fact that the cracks are still open at ambient temperature showed that the stress are still present, like the model is predicting. So, of course, it's only a starting point if you want to. There's room for improvement of the mechanical model, but that's what we have achieved so far. Thank you very much for your attention.